This is 7.4, and we're talking specifically that the book says we're talking about systems of inequalities and linear programming. And that sounds like a lot of mumbo jumbo, but it's actually not so different from what you've experienced in Algebra 2 and perhaps even Algebra 1. It's pretty similar along the lines of that. If you remember how to graph inequalities, then this should be a pretty straightforward lesson. It's just a little bit on top of that. There's only a couple extra things on top of that, but really, uh, when we get into the actual problems and the actual use of this lesson becomes incredibly useful because it kind of takes the stuff we learned in Algebra 1 and Algebra 2 and actually applies it to our lives and makes it purposeful. And indeed, when we actually get to what this is, linear programming, as we call it, is really not much more than just trying to maximize your profit or save money. And so it really is 95% of the time just all about making and saving money. Which you might think, well, I mean, that's not so relevant to all our everyday lives, I suppose, because we're not all business managers. But then, I started to think about how well, when I gave my whole life over to Christ, when I gave I committed my life to God, I gave everything over to Him, and I told Him, "You have everything now, not just my life, but you have my thoughts, my desires. You have my money. You have my all my possessions. It's all yours." And I gave everything over to Him, and I think as we ought to do. And so now what I have is an account at a bank that is stewarding His money, and I want to use it the best way that I possibly can. I want to be faithful and useful of it, like kind of like how with the parable of talents, the like the Jesus said, there's these people who gave them different talents. He says, I gave you this amount of money and gave you that much amount of money, and you should use it by the time I get back for the most good possible. For you should try to make it compound and do good things with it. And so I think about me and I'm like, man, I've been given an incredible amount of opportunity. Very few Christians in the world have the kind of economic surplus that we have here in Northern Virginia. And so I want to make sure that I use my money in a way that really glorifies Him. And I think about, well, hey, like what makes me happiest? I mean, I could try to be happy with a few more trinkets here and there. I could be happy with a new phone and a new gadget and all that sort of stuff. And that's all well and good. It's nothing wrong against that. But I don't know. I just feel like I'd be more satisfied with life if I knew that I was able to use this money to like build a well that people could use for literally forever. So they could drink water for forever. You know, or maybe there's a whole place that just you give money to a pastor and he'll build a well, and that uses this, and that's used to spread the gospel too, and that's doubly cool. Anyway, but I think Jesus talks about money, which I think is surprising that he talks about money literally more than anything else, literally more like more than heaven and hell. And if we think that, well, he came to talk about heaven and hell and save us from it, but he talks about money even more than that, as if he wanted to stress this is incredibly important. If you have resources, if you have money, you have to really, really be careful how you use it because for the rich people, the road is narrow for the to lead life, and very few find it. Um, so I really want to be a good steward of these things. Um, so what this lesson's all about though is really along those lines. Is like how do we maximize our maximize these accounts, maximize these resources we've been given for the most good possible. How do we like, for example, earlier I was thinking how can I structure my nutrition and the variables involved eating the right foods to have all your micro and macronutrients. How can I structure those things effectively so that I can spend the least amount of money having my nutrition and getting all the food I need in a day? And I figured if I'm able to do that and I'm able to live a satisfied, filled life of food, and I don't need to spend a bajillion dollars every week doing it, then I could use that money that I saved, because that money that I saved is in a sense, as I think Edison said, money saved is money earned, except it's money earned tax free, so that's cool. But I could use that money and I could help people with it. mean, you and I, we could, we could save homeless people that are around us. We could do that because we've been given these resources, if we're smart enough about it. Anyway, I'm going on a huge tangent, but I really hope you see the weight of this lesson. This is really, really helpful and important lesson. So without further ado, let's get into it. And again, it's pretty simple, and I think you'll catch on pretty quickly about how to do this well. So if I'm make sure that I have a good paper. Grids are important here. So let's start with the basics. Let's say we wanted to graph an inequality back from algebra 1. So if I had y equals, it had y equals 2x plus 3, or if I want to say, not just that, if I want to say y is greater than or equal to 2x plus 3, the way I need to fix this drawing mode. Don't want to draw off touch. There we go. If I want to graph y is greater than 2x plus 3, I would first draw my axes, and then I would graph the actual line 2x plus 3. So I'd graph 2x plus 3. So I started at 3, and then I'd go rise 2 and run 1. And so I'd kind of draw a line like this. And then there's a distinction we're going to make. Well, if it's a greater than or equal sign, then I do a solid line. If it's a less than or equal sign, then I do a solid line. That makes this a solid line. But if it's just a greater than or less than sign, I do a dotted line. The trick to this is if it actually says, if there's a line underneath the symbol, then you do a solid line. If there's not a line underneath the symbol, then you don't do a solid line, you do a dotted line. Okay, so for example, if this was y is, let me change the equation real fast just to kind of make sure you get this down. Y is greater than 2x plus 3, I wouldn't do this line here. What I would actually do is that I draw a dotted line. Okay. And we may be familiar with all this. So then the next step would be, now we plug in a point that's not on this line. We just choose any point that's not on this line and plug that into the equation. Usually 0, 0 is an excellent option. It's really simple and easy to work with. So if I was to plug in, say, for the point 0, 0, remember that point's right here. That's the origin. If I was to plug the origin into this equation, I get 0 is greater than 2 times 0 plus 3, which gives us 0 is greater than, let's see, 3. And now I've got a statement. 0 is greater than 3. If this is a true statement, that means I shade the side that has the origin, the side that has the point that I just tested. If it's not a true statement, that means that this doesn't work. This point is not somewhere in the solution. So that means I have to shade the other side. So in other words, this is not part of the solution because 0 is not greater than 3. 0 is less than 3. So if I was to graph this, I want to graph all the points where y is greater than 2x plus 3. I've got to graph the side that doesn't have 0, 0, because that side is not going to, that side is not the side that has 0, 0, and 0, 0 doesn't work. Another way to think about it is when you graph an inequality, you graph the line, and then either one side or the other side is going to be completely shaded. Every single time, one side or the other side is going to be completely shaded because that's kind of how the line is graphed. The line is trying to indicate everything beyond this boundary is shaded. And so what testing a point does is helps you determine, well, which side is it? Which side is it? Which side is shaded? And if in this case we found out that it's not the side that has 0, 0 in it, so we shade the other side. It's the boundary of that other side. Anyway, so that's how you graph one inequality. Let's say we had a different inequality as well. Let's say we had an inequality, let's say we're going to graph a system of inequalities, and I'll use green to graph the second one. Let's say it was, I don't know, y is less than or equal to 2x. Let's do 2x. Let's do negative 3x minus 2. Okay, a little bit different. So now we start at negative 2, and then we rise a negative 3 and run 1. So we go this direction. And because it is a solid line, it's a less than or equal to, I draw a solid line. Okay? Great. So now we're going to go ahead and test that 0, 0 point again. And we'll get 0 is less than or equal to negative 3 times 0 minus 2, which gives us 0 is less than or equal to negative 2. And now 0 is not less than or equal to negative 2, which means we shade the opposite side from the origin, which means we shade all of this. Okay, so now with a system of inequalities, this system of two equations, if I want to say both of these are true, I want to find the place where both of these are the case, or y is greater than 2x plus 3, and the place where y is less than negative 2x minus 3. We're going to find both those locations at once. Then I'm going to go to the place that's shaded twice, that's shaded by both lines, by both boundaries. So that would be this little section here. This is the section that's shaded in twice, and so this would be our solution set. This would be our solution set. You notice that this red line is also, so this green line over here is inside the purple, so this would actually also be included as part of the solution as well. But the purple dotted line, although it's in green, it's a dotted line, and the dotted line means it doesn't equal. So this line would not be part of the solution set. It's a little, just a really almost splitting hairs here, but all I'm saying is that that dotted line shows that we cannot find a point on that exact line. But for the green line, we could see, oh yeah, we could include points in the green line because the points in the green line are also in the purple area. Great. So I want to just, if I were to try to recreate this freehand, we would say this line up here, up to that point, and all of this. This would be the solution set. All right, cool. Let's see. So that's a system of equations. That's a multiple inequalities at once. Now let's look at linear programming. Linear programming is really the application of this. How do we use this? And usually, there's more we could go into, I suppose, but we really don't need to go too much into the algebra or just the numbers. We can go mostly just look at the graphs. That's what we're going to focus today, is just how the graphs look and what the graphs can tell us. So it makes linear programming a lot simpler. And so what we're going to do is, well, let's say we have two variables. Let's say we have two different products we're trying to compare. We're going to buy a certain amount of two different products and get, let's see, I don't know, a certain amount of nutrients from each product, from both products. And we need to go beneath some sort of cost threshold. We need to try to minimize our cost. We would use those two items as our variables. So we use those as our x and as our y axes. So it's not like, usually before we're used to the x-axis and the y-axis. We're used to the y-axis being like money, and we're used to the x-axis being, I don't know, time or something. And so those are common uses for them. And here, what we're actually going to do is we're trying to figure out something about money, and we're trying to figure out something about, how to minimize and maximize money. But because we have so many variables involved, we've got money, we've got these two products, we're trying to figure out more about money just by looking at the graph of those inequalities. The graph of those inequalities. And so we're going to, that's a lot of really heady stuff right now. When we get to the problems themselves, I'll try to make it more concrete. But as we graph two inequalities, let's say we try to we'll end up making equations, or we'll graph these inequalities. Say we'll make an inequality that looks like this, and see it shades all of this up here, and this tells us we need to have some amount of x and y that's above these two values. We need to have some x and y that is beneath these values. Let's say these values, and so we'll have something like that. And then we'll have another x and y that is more of like a cost threshold, and so that'll be something like this. And we need to have it beneath this cost threshold. And so we'll say, okay, our solution set, the solution of that satisfies all the things we need for what we're talking about here. Actually, this green goes all the way down, but that's a different something else. Is the solution set is this? Let's use an orange. Is this orange bit right inside here, the place where it overlaps all three of these? And when we look at the corners are going to tell us the specific places that are going to be the most helpful for us in figuring out how to maximize profit or minimize cost or something like that. So we're going to pay attention to these corners very carefully and see which ones kind of do we want. And again, as we go into concrete examples, I think this will clear up immensely what we're trying to do here. So just hang tight until we get to this problem, or just skip ahead to those problems if you'd like to. But as for me right now, what we're going to do is we're going to jump right into the initial problems, which I hope would be, a lot of it would be somewhat similar to what you've learned in Algebra 2, or perhaps even Algebra 1, and the rest, and the rest will just be more of the application problems that I do these well. Some of these problems. Well, let's first off, let's go into number 1 and see a little bit more about what number 1 is like. Number 1 says match inequality with its graph, indicate whether the boundary is included or excluded from the graph, and do not use a graphing calculator. Okay, now because we cannot graph solid lines and dotted lines, things are going to be a little bit different in this particular graph. They're going to say, or in this particular program, so they instead of saying like dotted line or solid line, you can see that in the graphs they give us, they can't really show us a dotted line or a solid line. And so they're going to ask us, is the boundary included or excluded? So in other words, when they say if the boundary is excluded, that means you got a less than or a greater than sign, because it has a dotted line. If it's saying the boundary is included, that means you got a less than or equal to or greater than or equal to sign. So it's got a solid line. That's what we're trying to communicate through its inability to graph that dotted line or solid line. That's all that is. But all it's really asking here is first is saying match each equation with a graph, and then indicate whether it's a dotted line or a solid line. So cool. We'll start with the first one. Y is greater than 2 minus x squared. You can remember what this looks like a bit from transformations, what this looks like as a graph. So we'll say y is greater than or equal to 2 minus x squared. This is, let's see, what has happened here? We've taken x squared and we've flipped it upside down. That's a negative x squared. We flipped it upside down and we've added 2 to it. We did a plus 2. So total transformations is we've flipped it upside down. So flip across x axis. And then we add 2. We go up by 2. So that's all we're doing. And then you can see the graph that does that the best is E here. And you'll see that it also graphs the outside, not the inside of the line. Let's see why that is. When we plug in the point 0, 0, and plug in the origin, which is right here on the graph, that little purple spot I just made, we can graph this, and this will be 0 is greater than or equal to 2 minus 0 squared. So we get 0 is greater than or equal to 2, but 0 is not greater than or equal to 2. So because 0 is not greater than or equal to 2, we can't shade this section. We got to shade the outside section. So this inside section is not shaded. We shade the outside section because 0 is not greater than or equal to 2. And so this would be the answer. All right, cool. So we'll take the first one. Y is greater than or equal to 2 minus x squared. And let's see, is it included or excluded? We'd say because it's got a solid line, because it's got a greater than or equal to, it's got a solid line, so that means it's going to be included. It's going to be included. Okay. All right, let's look at the next one. So we did that one. Check. And then 2x minus 6y is greater than or equal to 2. If you're astute, you might notice that is a line in standard form. Okay, let's look at what that graph looks like. First, we're going to change that to slope-intercept form so we can kind of see what it's doing. And we have, let's see, 2x minus 6y is greater than or equal to 2. So we'll go ahead and change the slope-intercept form. So negative 6y is greater than or equal to 2 minus 2x. We can switch the 2x and 2, so negative 2x plus 2 greater than or equal to, is less than or equal to negative 6y. Divide both sides by negative 6. And so we get y is great. Oh, we divide by negative 6, so we're going to switch the sign. Don't want to forget that. That's very important. Whenever you divide or multiply by a negative number, you switch the sign. So we'll do 6. When we divide, we get y is less than or equal to 1/3 x minus 1/3. And if you're curious as to why we switched the sign, just as a quick refresher, it took me a while to really understand the intuition as to why do we do that? What's the point behind it? If we say something like 0 is less than 4, or let's make it even, let's not just make it a 0 because that might be confusing. Let's say 1 is less than 4. That's a true statement. Now, if I multiply both sides by a negative number, let's say -1, I get -1 is less than -4. Well, that's not a true statement. -1 is definitely not less than -4. -1 is greater than -4. So we got to swap the sign to really understand that. And so when you actually look at a number line, what we're doing is you can see that the positive numbers are greater if you get a higher number. So on the positive side, we have a higher number is, let's say 6 is going to be greater than 3. So 6 is greater than 3. But if you look at the negative side, the bigger numbers, the absolute value of the bigger numbers, are actually less. So we say -6 is less than -3. This -6 is less than -3. They're kind of the same because the numbers are swapped. It's you go -6, -5, -4, -2, -2, -1, 0. It goes backwards instead of forwards. 0, 1, 2, 3, 4, 5, 6. The sign has to go backwards when you change everything to the negatives. And so when we multiply by negatives, the sign has to flip to compensate for that. We just switched realms right now. We went from the positives to the negatives. Anyway, I hope that was a big tangent, but that really helped me understand what's going on and why that's happening. Why we have to switch that sign when we multiply by negative. Anyway, so we got y is less than or equal to 1/3 x minus 1/3. So if I were to make a graph, we'd start like say 1/3 or -1/3, and we would go up very slowly, rise 1/3, run 1, or rise 1, run 3. So something like that. It's an equal sign, so we include it. We have a solid line. There's a less than or equal to, so we include the solid line, and then we need to test a point. So we'll do, let's say, the origin. 0 is less than or equal to 1/3 times 0 minus 1/3. So we get 0 is less than or equal to negative 1/3. And is 0 less than or equal to negative 1/3? No, it's greater than or equal to. So we got to sketch the other side, just like that. And it looks like the graph that matches that best is B. So plug that in. 2x minus 6y is greater than or equal to 2. And then we'll say it's included. All right. Now, x is less than or equal to 2. This one is a rather straightforward one. So we'll say x is less than or equal to, well, I mean, depending on how well you liked it during algebra class. X is less than or equal to 2. So if we have a graph, we go to 1, 2. That means that we're going to draw the line. It doesn't matter what y is. X is always going to be less than or equal to 2. So if I was to graph this for the points, let's say when y is 0, x is equal to 2. When y is 7, x is equal to 2. When y is -3, x is 2. So our line is going to be like, hopefully a straight line. If I could actually draw a straight line, this would be our line. And it's got the equal sign, less than or equal to, so we're going to draw a solid line on a dotted line. Now to test which side we draw it on, now to test which side we shade, we plug in origin, so 0 for x, 0 for y, so we get 0 is less than or equal to 2. 0 is less than or equal to 2, so we'll shade the left side. Okay, let's see, we'll match it up with the graph. That matches up best with C, so we'll get x is less than or equal to 2 for C, and then because there's an equal sign, we'll say it's included. The boundary is included. Okay, let's do the same thing with y. Y is greater than 2. That means it doesn't matter what x is, y will always be, well, if we were to graph just the equals version, which graphs just the equation, we get y would always equal 2. So we'd start at 2. But remember, this is a less than, it's a greater than, it's not a greater than or equal to, so that means you got to do a dotted line. So we'll have to do a dotted line at 2. Because we're doing the same thing as x is less than or equal to 2, except now we're dealing with y. So we're switching from from vertical to horizontal. So this would be the line. Now we need to figure out which side to shade, we plug in 0, so we get 0 is greater than or equal to 2. 0 is not greater than 2, so that means that I cannot shade the side of the origin, I have to shade the side above it. So that's this top side here. So that gives us it gives us f. So we'd say y is greater than 2 is f, And because it is not greater than or equal to, it doesn't. We don't have a solid line. We've got a dotted line. That boundary line is excluded. Okay, that one's that. So let's see. We've got x squared plus y squared is less than 1. Now, if you wanted to graph this one, you may recall this is the shape of a circle. X squared plus y squared equals r squared. This is the shape of a circle. X squared plus y squared equals r squared. And so our radius is our radius squared is 1. R squared equals 1, which means our radius is 1. So we got a circle with radius of 1. So we can just, if we were to draw this, we would just draw a circle with radius of 1. Now this is not just that. It's less than 1 though. So if I graph this, and this is where this might be a little bit different from algebra, because you're used to drawing graphing lines, but now we're doing things like curves and inequalities and curves and and specifically in this case a circle. So we do x squared plus y squared is less than r squared, or is less than 1. So we got to test a point. So x squared plus y squared is less than r squared, or in this case less than 1. So we'll plug in 0 and 0. So 0 squared plus 0 squared is less than 1. So 0 is less than 1. 0 is indeed less than 1. So we shade the inside of this circle with a radius of 1. It's a pretty lopsided circle, but I hope you get the idea. Let's see. So we plug in, so that's A. That's A then. Let's see, x squared plus y squared is less than 1. And because we don't include the edges of the circle, because it's not less than and equal to, it's just less than. Yeah. So when I was graphing this, it's probably better to make this clear. We'd draw a dotted line around it and then fill it in. That means the boundary is excluded because it's less than, not less than or equal to. Excluded. Not less than and equal to. Okay, the last one. Well, this goes in a pretty obvious place in D, but let's just kind of see what it looks like. Y is greater than 1/2 x minus 1. So this is taking that graph. Y is greater than 1/2 x, or y is equals x squared, that x squared graph. So greater than 1/2 x squared minus 1. We'll take the x squared graph. What it means is that we're going to go down 1, and we're going to shrink it. We're going to compress it by a factor of 2. Or in other words, we're going to lengthen it by a factor of 1/2. And either which way, we're going to compress it. So we're going to go down 1 and kind of make it wider. Wider, kind of like that. Okay. Now we test that origin point again to see if we graph the inside or outside. Sorry, because this is a dotted line, because it is greater than, not greater than or equal to. So we'll graph just the dotted line because it doesn't include the boundary, and then we'll have 0 is greater than 1/2 0 squared minus 1, which gives us 0 is greater than -1, and 0 is greater than -1, so we will graph the inside. And that fits very nicely with D. So we'll say, let's see, y is greater than 1/2 x squared minus 1, and because it's not greater than and equal to, we'll say boundary is excluded. Great. All right. Number 2 then. Graph the inequality. 5x plus 6y is less than or equal to 30. So this is a pretty straightforward problem. We're going to just follow the same steps as before. This should take a lot less time than number 1. This should be 5x plus 6y is less than or equal to 30. 5x plus 6y is less than or equal to 30. So we'll just solve for y. So we can put it in slope-intercept form, make it easy to graph. So we'll do 6. You could also do point slope form, of course. We're going to do this, 30 minus 5x, and we can do 6y is less than or equal to -5x plus 30. Divide both sides by 6. We're dividing by a positive, so we don't have to switch the sign or anything. So we'll say divided by 6. divided by 6. So we'll get y is less than or equal to negative 5, 6x plus, let's see, 30 divided by 6 is 5. Okay, so we'll go to 5. We'll start at the point 5, and we'll graph the rise over run is negative 5, 6. So we rise to negative 5, so that means we go down to the origin, and then we go over 6. So we go rise, we fall 5 and run 6. That'll bring us to that point there, and we graph. We'll just combine these as best as we can, like so, and that should be our graph. Now, this is because it's less than or equal to, we keep this solid line, we don't use the dotted line. And then finally, we just got to figure out which side to shade. So we'll plug in zeros on both sides. You can do it with the beginning equation or the manipulated equation. You could say 5 times 0 plus 6 times 0 is less than or equal to 30, but I'll plug it into the bottom. So we'll have 0 is less than or equal to negative 5, 6 times 0 plus 5. So 0 is less than or equal to 5. 0 is indeed less than or equal to 5. So we'll graph the side that has 0, 0, has the origin. We'll shade this whole portion here. And that's it. That's it. That's the answer. We're done. Okay. 3. Graph the inequality. Again, y is less than x squared plus 6. So we'll just start with, this is the same thing as x squared. We just need to, we just push it up by 6. So remember what x squared looks like. X squared looks like we have 0, and then at 1 we have 1, at 2 we have 4, at 2 we have 4. Yeah, I don't know why I graphed 3. There it is. I need to graph 4. And then at 3 we have 9. So 9. So that's what the graph usually looks like, and we mirror it on the other side. However, now we're going to move all these points up 6. So we will take let's take this, I guess it's green. We'll start at 6. We'll go this direction, and then let's see, 1, 2, 3, 4, something like that, and then mirrored on the other side. There we go. All right, and then I'm going to go ahead and combine this into a line. It's less than, so not less than or equal to. So we'll just graph a dotted line to combine these points. Okay. Not the best dotted line, I know, but it'll do the job. Okay, now we got to figure out if this graph is, if we shade the bottom portion or the top portion. So plug in zeros and say 0 is less than or equal to 0 squared plus 6. So 0 is less than or equal to 6. 0 is indeed less than or equal to 6. So that means we shade everything beneath this graph. So all this, I can just draw long lines. I hope that gets the point across. We're graphing all of this. This is the whole thing. Okay. So that is number 3. Simple as that. Just gotta graph the transformation and then follow the extra rule or two for an inequality. Number 4, graph the inequality. This is y is greater than 7 to the x power. Okay, this is going to be a little bit strange, so it's best to just pick some points and try to graph each point. So we'll start with, and then combine them into a line. So let's just make a little table here. Let's say we've got x is, let's start with I don't know, negative 2. Let's say negative 2, negative 1, 0, 1, and 2. That should give us a good approximation of what's going on here. Okay, and then y, let's see, y is, if I was to graph the actual line, now I'm just worried about the line now, not the actual shading yet. So I'm trying to just figure out what the line would look like if I was to graph y equals 7 to the x power. So that would be, let's see, negative 2 would be y equals 7 to the negative 2. So that'd be, this would be y equals 1 over 49. So 1 over 49, so really, really small. Negative 1 would be y equals, let's see, so that'd be that. Then negative 1 would be y equals 7 to the negative first power. And so that would be y equals 1 over 7. Okay, so it'd be 1/7. And then 0, we'd have y equals 7 to the 0 power, so y equals 1, so that's 1. For 1, we have y equals 7 to the first power, so that's just 7. And then y equals 7 squared would be 49. Wow, that goes up fast. That escalates quickly. All right, so we have, let's see. So let's just graph these. So -2, we've got -49. So as close as I can get to that that bottom line without actually touching it. And then we have -1 is -7, a little bit closer up, but not really much at all. There we go. And then 0, we have 1, 1 we have 7, and then 2 we have 49, which I can definitely not graph. Okay, so this is the graph of the line. We know it's not, it doesn't include the boundary because it's a greater than, not greater than or equal to. So we'll have a dotted line here to graph it. We'll graph this as a dotted line, just like this. And this goes up really fast. Okay, so that's kind of the graph of what that looks like. Now we just need to figure out which side to shade. So we'll plug in zeros. So we'll get y, or sorry, we'll say 0 is greater than 7 to the 0 power. Will that be 0 is greater than 1? Well, 0 is not greater than 1. So that means we cannot include the origin. This is incorrect. So that means we cannot include the origin to shade the other side, which means to shade this side. All of this up here. Okay. And that's it. That's our answer. Cool. Number 5. Graph the solution set of the system of inequalities. Okay. So remember, this graph the solution set, we've got to graph each inequality, and then we have to find the places where they overlap, and that's the solution set. All right. So we'll start with the first one. 3x minus 4y is less than or equal to 12. So 3x minus 4y is less than or equal to 12. This, if I was to move it over, if I was to kind of readjust it, so it's in slope-intercept form, this would be -4y is less than or equal to -3x plus 12. And then we divide by -4. Remember, we switch the sign, so we get x is greater than or equal to 3/4 x plus, oh, not plus, it'd be minus 3. Okay, so that's the first graph. Let's go ahead and start by graphing that first graph. We start at -3, and we rise over 1 is 3/4, and we do a solid line because it's greater than or equal to. So rise 3, run 4. 1, 2, 3. 1, 2, 3, 4. Great. And so we'll just rise 3, run 4 a bunch of times, and we'll do that. Maybe we'll see rise 3, run 4, and rise 3. Oh, I can't go. Yeah, I can go one more. Rise 3, run 4, and then all the way down. I just want to be very precise about this so I don't mess anything up. Okay. Yeah, fall 3, retreat 4, I guess, is what you would call it. Fall 3, retreat. That sounds very pessimistic. The very pessimistic way of graphing an equation is by retreating 3 and falling 4. Or falling 3 and retreating 4. Okay. It creates the equal sign, so it also includes the equal sign, so we're going to go ahead and include this line in here. Am I graphing green now? Why is this green? That was just purple a second ago. Hold on. I want to make this not confusing. I'm going to make that purple real fast. There we go. That's better. And then I'll take blue and I'll graph the other equation. No, this is purple. Thank you. Okay, and then I'll take blue and graph the other equation. 4x minus 2y is greater than 8. Let me erase that dot. Okay, and well, this will be -2y is greater than -4x plus 8, and then we have y is less than 2x minus 4. So that gives us, let's see. So that means we start at -4. We do a before before we even graph this line. Oh, I've totally forgotten. I need to shade one of these sides of this equation. I'll actually do the shading in a second, just to make it all clean and clear. So we'll do y is 2x minus 4. So we'll start at -4, and we'll rise 2, run 1, rise 2, run 1, and so on. And I think I can just see where the points are. But this is a dotted line. Oh man, this is a dotted line. It's not a solid line. I gotta be careful. So this becomes a dotted line. something like that, all the way up. Okay, and then we go down and down all the way to the bottom. Great. All right, now shading. Which side do we shade, or where do we shade? Well, we know that for the purple, let's see which side we. Let's see if we let's see if we shade the side with the origin in it for the purple. We'll do. What? Why did I? That's a Y. Those are Y's. If you're worried, if you're concerned, because I'm concerned about myself right now. So 0 is greater than or equal to 3/4 times 0 minus 3. So that'd be 0 is greater than or equal to -3. Well, 0 is greater than or equal to -3, so that means we're going to typically shade this top side over here, which includes all of this in here. So that means we're going to shade all of this. And then for the blue, we're going to look at it this way. We'll say 0 is less than 2 times 0 minus 4. 0 is less than -4. Well, 0 is not less than -4. So we don't, 0 is not less than -4, so we don't shade the side with the origin in it. We shade the opposite side. So that means for blue, we'd shade all of this. Now remember what I said, the answer is the section that overlaps. The section that completely overlaps, that'd be our answer set. So our answer set is not any of this stuff up here. It's not any stuff down here. It's just that section in the middle. This is right here is our answer. Okay, that's their answer right there. Okay, great. All right, so I quickly checked with number 6 just to make sure there wasn't anything weird going on with what they're looking for here, because this trying to find an algebraic method to solve a system of inequalities is it's a weird thing to ask for, because this right here is the algebraic solution. This is the solution set. We would officially say this is the solution set of the system of inequalities algebraically. You could go a little bit further, I suppose, and you could plug in y equals x squared to x squared plus y squared is less than or equal to 9, and you could plug that x squared in for y, and you could try to find out the vertices where they intersect, the intersection points of these two graphs, but that doesn't help you find that's not what we're trying to do here. We're trying to find the shaded area that covers both of these things. So, and I looked at their guide and all that. Yeah, all they're asking you to do is, this is the exact same problem as the rest of the other problems. Just graph them, graph both of them, find the place they overlap. Cool. That out of the way. Let's graph these two. So you get x squared plus y squared is less than or equal to 9. So that means, let's see, x squared plus y squared is equal to r squared. That is the graph of a circle. So if we know we have x squared plus y squared, this is a circle. So r squared equals 9, which means the radius equals 3. All right, so our radius is 3. We can, if you want to be really technical, you could say it's plus or minus 3. And that would also work. That'd work great, and that would do the same circle. If you graphed at the radius of -3, it'd be the same as the graph of the radius of 3. Anyway, so we'll go ahead and graph this. It's less than or equal to, so we'll do a solid line right around 3, just like this. Okay, perfect. That's the first graph. The second graph is y is greater than or equal to x squared. So to graph that, we'll just graph y equals x squared. So let's see. We've got a point at 0, 0. We've got a point at 1, 1, 2, 4, 2, 4. And then, let's see, 3, 9. That's 3, 9. And then 4, 16. We can't quite graph that, but we're getting really close. Anyway, I'm going to copy this on the other side as well. So 1, 1, all right, let's see, -1, 1, -2, 4, -3, 9, and then -4, 16. Okay, great. And because it's a greater than or equal to, we're going to do a solid line to graph it up. And, oh, that's a bit over. That's over there. I graphed a little bit off there. There we go. That's better. And then on the other side, the same thing. There we go. And there it is. Cool. All right, now we just got to figure out where to shade. And that's the next section here. So we've got, let's see, if we plug in the origin, we can plug in the origin for the circle. We can't plug the origin in for the parabola, and I'll show you why in a second, why that doesn't work so well. So we have 0 squared plus 0 squared is less than or equal to 9, so 0 is less than or equal to 9. So yeah, 0 is less than or equal to 9. That means that we include the origin, which means we include all of this interior stuff, including right there. Great. And then for the blue one, we have to choose a point that's not on the line itself. If we chose 0, 0 itself, we get y is greater than, or we get 0 is greater than or equal to 0, which is true, but that doesn't tell us to, that would tell us to shade the side with the origin on it, but the origin's right on the line, so which side do we shade? I don't know. So let's choose a different point. Let's try, let's say 0, I don't know, 1. Let's try 0, 1 as our test point. We tried that, then x is 0, y is 1, so 1 is greater than or equal to 0 squared, and so we get 1 is greater than or equal to 0, so that is true. That's also a true statement, which means we shade everything that contains the point 1, 0, or sorry, 0, 1, which is that point right there, which means we include this here, and all this up here. Okay, so now that we've gotten that, we've done all the shading we need to do. We just find the place of the overlap. Well, the place of overlap is that purple and blue place, so we can get rid of all of this shading. And if I can do this carefully, there we go. Then that is our answer, that center piece in the middle. That center area is our final answer. Up here, down there, and everything in between. That's our answer. Cool. Number 7. Graph the solution to the system of linear inequalities. This is the same problem as all the rest of them, except now we just have more things we need to graph. So we need to find the way it overlaps with all of these, not just 2 of them, like all 4 of these. Okay, so x is greater than 0, y is greater than 0. I'm going to use, let's say black, to do x is greater than 0 and y is greater than 0, greater than or equal to 0, just because it should be pretty self-explanatory. Well, I don't even know self-explanatory, but it should be pretty clear on what side is shaded here. So if it's y is greater than 0, it's going to be all the right side. If it's x is greater than 0, it's going to be everything above x, the x-axis. So really what we're dealing with here is this section that is right in the center, this first quadrant of the system, because that's the place where x and y are both positive. They're both greater than 0. So we're dealing with that also, as well as the x and y axes, because it could be x equals 0, y equals 0, because x is greater than or equal to 0, y is greater than or equal to 0. Okay, so now we know it's that first quadrant. We're going to just forget the rest of the quadrants. We're going to look just at that quadrant and graph the next 2 equations. So 8x plus 2y is less than or equal to 16. So that gives us, let's see, 2y is less than or equal to negative 8x plus 16, or y is less than or equal to negative 4x plus 8. So I graph that. We start at negative 4. No, we start at 8, and then we start at 8, and then we drop 4, run 1, drop 4, run 1. Okay, and so we draw a solid line because it's less than or equal to, and we'll do it with the shading in a second, in just a bit. There we go. Okay, that's our first line. And then the second line, let's make that blue. We have 3x plus 4y is less than or equal to 12. And so we'll graph 3x, or we'll say 4y is less than or equal to negative 3x plus 12, or y is less than or equal to negative 3/4 x plus 3. Okay, so start at 3, and we'll rise a negative 3, run 4, and we will graph that line there. If you're really astute with standard form, you might notice that when we say 3x plus 4y, it's giving you the x and y intercepts. If you hadn't learned that in algebra already, see this is you can tell that our x-intercepts is, or our y-intercept is at 3, and it gives us 3x. Our x-intercept is 4, and it gives us 4x. Our x-intercept for the purple line is 2, so it gives us 2y, and then our x-intercept, or y-intercept for the purple line is 8, so it gives us 8x. Just kind of a little tidbit. That can make things a little bit faster if you wanted to graph things just a little bit more quickly. But I'm kind of going through the slope-intercept form because that's kind of what we're used to. Okay, so we note the answer is only in that first quadrant, somewhere in the first quadrant. So we're dealing with just that because of the x and y parameters. Now let's see which sides we shade for the purple and green line, purple and blue lines. If I plug in 0 is less than or equal to negative 4 times 0 plus 8, we get 0 is less than or equal to 8. 0 is less than or equal to 8, so that means we graph everything beneath the purple line. All of this, all of that. Okay, but we're gonna stay in the first quadrant again because of x and y. All right, and then we'll do 0, or 0 is less than or equal to negative 3/4 times 0 plus 3, or 0 is less than or equal to 3. And let's see, 0 is indeed less than or equal to 3, so we'll graph all the things that have that 0 inside, but I'll just skip everything that's outside the first quadrant because it's not necessary. And so we can see the solution set is this section in the center, is this right here. This is our solution. All right, and so I want to see if I can erase this stuff in the center, this stuff here, without erasing too much of my line, which just seems kind of difficult now that I'm thinking about it. There we go. And about that blue line. There it is. So that's the answer. Okay. Number 8 is a little bit of a weird question, so it has a little bit of a nuance to it. And I think the hardest part about it is just understanding what the blanks mean. But it says, write a system of inequalities whose solution is the region shaded in blue in the green, in the given figure, not green figure. All boundaries should be included. Okay. So let's see. Look at the first thing you want to notice is that we're dealing with just the first quadrant. This is all just quadrant 1. It's not going outside here, it's not going down here, so we can see that x, it's all the values of x is greater than 0, and the values of y is greater than 0. So all this stuff, y is greater than 0, and x is greater than 0. That's all this blue stuff here. So we can initially start off just by saying, well, in this graph, x is greater than or equal to 0, y is greater than or equal to 0. Because it looks like we're also including the lines y equals 0 and x equals 0 in this. Okay. First off, well, actually, before we can go any further, you can see this. I'm just jumping to the option A, because it says option A is this is the answer, or option B is that there is no solution. Well, we can see there's a solution. There's a solution right here. That's the blue stuff. The blue stuff is the graphical solution. So we can tell there's definitely a solution. We just got to figure out what it is, as far as an algebraic set of equations looks. So I'll plug in. We've got 2 of them already. We know it's greater than it's x is greater than or equal to 0, or y is greater than or equal to 0, 2 of them. And you can notice the other 2, you can kind of get a feel for what the other 2 lines look like. It looks something like, one of the lines looks kind of like this, and the other line kind of looks like this. So if we can figure out what these lines are, then we can figure out these graphs. That's what we need to do. So we'll just go ahead and figure out these lines. Let's see, we've got 2 points on each of them. The first one, let's look at the blue line first. Let's see, it starts at y equals 7. So y equals 7. So that'd be the point, or more accurately, 0.07. And that coordinates very well with this one here. Just to be clear of what they're asking for, they want, in the first blank, they're asking for, is it greater than, less than, or equal to, what's going on there? And then for this one, they want a greater than, less than, equal to, what kind of something there, something like that there. But for the second blank, they want a number, some sort of coefficient to multiply x by. All that said, let's just go ahead and solve this equation and figure out what this equation is. We've got 2 points, so we can find. Let's see, we know that y-intercept, if we can find the slope, we write this in point slope-intercept form. So we know this is, the blue line is y equals some slope times x plus 7. And let's see, we can plug in the 0.56 to find this slope. So we'll say, let's say 6 equals the slope times 5 plus 7. So we'll subtract 7 from both sides. So we get -1 equals 5m, so we get -1/5 equals m. Okay, so our equation for the line itself, for the actual line itself, is y equals -1/5 x plus 7. Now bear in mind that is not the the inequality because this is just an equation. But now I've got this equation. This equation here is y equals negative 1/5 x plus 7. That inequality will tell us which side to shade. We know that we're including the line itself. We can tell because this line here is a solid line. It's not a dotted line, so we're including this line. So it's either greater than or equal to or less than or equal to. So that helps us narrow that down. Then we also know that the solution also has 0, 0 work. Okay, so we need to figure out some way to make it so that 0, 0 works. So let's plug in 0, 0 and see where that happens. If we plug this in, we have y and something. The actual solution, the actual inequality is y is something of 1/5 x plus 7. It's either greater than or equal to, less than or equal to, or that's it, less than or equal to, or greater than or equal to, because it's got that solid line. Okay, so plug in zeros, we get 0 is something 1/5 x 1/5 times 0 plus 7, or negative 1/5, excuse me, it's negative 1/5. And then we get 0 is something to 7. Well, we'd say 0 is less than or equal to 7. So we'd say less than or equal to. So that means this answer is y is less than or equal to negative 1/5 x plus 7. That's our final equation. Y is less than or equal to negative 1/5 x plus 7. And that gets us this shaded region down here. So that's what we've got over here. And you can tell for the purple line, we've got all this going on here, because that covers the blue area as well. Okay, so let's go ahead and figure out that's the blue line. Let's go figure out the purple line. And fortunately for us, it actually gives us the equation, the purple line. It just tells us it's something. So y is something times of negative 6/5 x plus 12. So we'll just plug it in. We'll say y is something negative 6/5 x plus 12. If we plug in zeros, if we plug in origin, we get 0, something negative 6/5 times 0 plus 12. So we get 0 is something and 12. And we'll say, what is that? To make that true, we need to say that 0, because we want to include the origin is part of the solution set. So we've got to make sure that it's a true statement when we plug this in. So we'll say 0 is less than or equal to 12. We said, again, equal to because it's got a solid line down there. It's got a solid line. And we'll put less than or equal to because that makes it a true statement when we plug in 0, 0. Okay, so y then is less than or equal to, our full equation is y is less than or equal to negative 6/5 x plus 12. So our answer is less than or equal to. And that's our answer. Great. Okay, 9. Find the minimum and maximum, if they exist, of the objective function f subject to these constraints. We want to find the minimum and maximum of the function f equals 5x plus 4y when x plus y is less than or equal to 9, x minus 3y is less than or equal to 0, and when x is greater than or equal to 0 and y is greater than or equal to 0. So we're going to start off just by graphing these equations and just seeing what that takes us, what that does for us. Okay, so let's start here. So let's start by graphing these constraints here. So we've got x plus y is less than or equal to 9. So that gives us y is less than or equal to negative x plus 9. So we'll go to 9 and we'll graph negative x, negative 1x. And it's less than or equal to, so draw a solid line, something like that. This looks about right. And there we go. And then let's see, do we plug in 0, 0? If I plugged in 0, 0, actually, we'll get to that in a second. X minus 3y is less than or equal to, no, wait, no, we want to do that. Let's graph that. Well, if we graph 0, 0, it graphs this whole section, because, let's see, 0 less than or equal to 0 plus 9, 0 is less than or equal to 9, 0 is less than or equal to 9, so we graph that bottom section there. Great. And then the next one, maybe do that one in blue, will be x minus 3y is less than or equal to 0. So that gives us, let's see, negative 3y is less than or equal to negative x. Divide both sides by negative 3. So we'll get y is greater than or equal to 1/3 x. Great. And that seems to be about right. Yeah, so we'll graph that. So we start at the origin. Because the y-intercept is 0, rise of run 3, and say it has an equal in it, so we'll draw a solid line. Okay. Really like when they give us grid lines here. This really helps. Okay. And then let's see, we can't test the point 0, 0 because that's just on the line itself. We can test the point 0, 1, that'll work. That point 0, 1. And let's see, so that'd be plugged in 0, 1, that'd be 1 is less than or equal to is greater than or equal to 1/3 times 1/3 of 0, which gives us 1 is greater than or equal to 0. That's true, so that means we graph this top section over here. Okay, so right now you can already see the sections overlapping is that top left section, and that's what that's going to be part of our solution set here. And then finally, we've got x is greater than or equal to 0 and y is greater than or equal to 0. Okay, so x is greater than or equal to 0. X is greater than or equal to 0, and y is greater than or equal to 0. So that's just that's quadrant 1. So if x is greater than or equal to 0, so if x is greater than or equal to 0, that means we graph this entire top portion, which means that again, that means the only thing that we exclude at this point, at this point, it means the only thing we exclude is that excludes this bottom section down here, this section I'm putting in green. Everything else is still included. Everything else, the solution set so far is included, because the solution set so far has been this. That's been the solution set so far, and everything inside that. So we didn't really cut so much off there. But if we do y is greater than or equal to 0, let's see. Then we start the y-axis, and then we're going to go greater than or equal to 0 on the y-axis, which means we cut out a whole chunk. So it used to be, this is the answer. Now, we're going to get rid of all that left section. So it's just going to be, the place that overlaps is just this section over here. This just here, just the first quadrant. And that's kind of what x is greater than or equal to 0 and y is greater than or equal to 0 is. Great. All right, now that we have the triangle, how do we find the minimum and maximum values of this function? So we have, this is a linear programming problem, and it'll make sense more, I think, when we get to the actual real-life examples. And I just discovered this year when I was trying to figure out the fastest way to get from point A to point B in driving, and that trying to find out if there's a specific points in a set of places you can start with that's faster or best. And the point of the matter is, I found out, and this is the way it is that the corner points are the only points. It doesn't matter what function you have or what goal you have, these corner points of your solution set are going to be the only possible places that you're going to have anything valuable, or any answer to any solution, or any minimum or maximum, or anything like that for any purpose. It's always going to be one of these corner points. None of the others are going to be really that helpful. Okay, so we need to figure out what these corner points are, so that we can figure out where our minimums and maximums are. And I want to show you how to get to the minimums and maximums in just a second, but let's find the corner points. The corner points are let's see, the one of them is 0, 0. Another one is, let's see, that looks like 0, 9, is that right? Yeah, that'd be 0, 9. And this last one, what is that last one? That would be, let's see, that's the intersection of the blue line and the purple line. Let's see, so that'd be the intersection of these two lines right here. We got to figure out where these two lines intersect. So let's go ahead and just calculate that, what that is, the intersection of those two lines. We can use substitution to do that well. We can substitute, let's see, if x plus y is less than or equal to 9, then we'll say that y is less than or equal to negative x plus 9. So I can plug that into the other equation. So we get x, we'll say x is x minus, let's see, I hope I'm using the right colors, I'm not swapping the colors incorrectly. I think I'm doing that right, yeah. X minus negative x plus 9 is, or minus 3 times that, 3 times negative x plus 9 is less than, is equal to 0. Actually, I use a less than or equal to sign. We're just trying to find the intersection point of these two lines, and so we're trying to find the intersection of the equations themselves. So we can choose equal signs here. Trying to find the intersections of the lines, not the actual shaded regions. So we'll use equations. So we get x minus, so we get x minus or plus 3x minus 27 is equals 0. And then we add, so we get 4x equals 27, and then so we get x equals 27 over 4. Okay, 27 divided by 4, you can probably do that in your head, but just to be pretty precise, there's no question, is 6.75. So x is 6.75. Y then, let's see, it's x is equals 6.75. Let's see if I can plug that back in to figure out what y is. So we get 6.75 plus y equals 9. So 9 minus 6.75 would be 2.25. So y equals 2.25, which means this point right here is 6.75, 2.25. That is this point right there. All right. Good. So we've got our 3 points. Now, what is that useful for? What am I trying to do here? Well, our objective function this entire time, the function we're trying to find the minimums and maximums for, is the function is 5x plus 4y. We're trying to find the minimums and maximum values that come with 5x plus 4y. And the only values that are really going to be important to us, that are going to be really helpful for us, are these vertices. That's the only things that are actually going to give us anything meaty or weighty to work with. So let's look at them. F equals 5x plus 4y. Let's test each one of them and see what value we get when we plug in each of these points. So if f equals 5x plus 4y, we can test that and see what values we get. So we get, for the first one, we get f equals 5 times 0 plus 4 times 0. So that equals f equals 0. So that seems pretty small. Then the second one, we get to f equals 5 times 0 plus 4 times 9, which gives us 36. And the last one, we get f equals 5 times 6.75, and then plus 4 times 2.25, which equals, let's see, 5 times 6.75 is, oh no, this would have been faster to do in my head at this point. 33.75, and 2.25 times 4 would be 9. So 33.75 plus 9 would be 30. That would equal 42.75. Okay, so our maximum, the maximum value we get for f is when we plug in that corner point, that 42.75. This is the maximum. And let's see, the minimum is that just this 0. That's the lowest value we get with f. So if I plug in these 3 corner points, the minimum value we can get for f is 0. The maximum value we can get for f is 42.75. So that's our answer then. So our minimum is 0. That's the minimum value we can have for f, and we have that value at 0, 0. And I guess you could, if we went into 3 dimensions, this could become even clearer and more intuitive. Unfortunately, we don't. Well, actually, maybe not unfortunately. Maybe fortunately for you, we're not going into 3 dimensions here. We're just going to stick in 2 dimensions. But we could actually make a 3-dimensional graph out of this to kind of just see f and see where f is. But because we're not in 3 dimensions, it looks, we can't quote unquote see what f is doing and where f is and how high or low f is at any given point. We just got to test the points out. So all I'd say, that's why this might seem a little bit confusing at first, because it's like, well, we're trying to do a 3-dimensional thing in 2 dimensions. But anyway, our highest point is 42.75 at the value 6.75, 2.25. And that's the answer. Okay. Number 10. We finally get to an actual application problem. This might actually make a little bit of sense. And this is actually an application problem that applies to me. So this is interesting. Mary's diet is to contain at least 24 units of carbohydrates and 19 units of protein. You should actually say grams, it's fine. Food substance A costs $1.40 per unit, and each unit contains 3 units of carbs and 4 units of protein. Food substance B costs 80 cents per unit, and each unit contains 2 units of carbohydrates and 1 unit of protein. This gets really confusing when you're trying to do with all the micro and macronutrients at once. You get like 26 different things, and then you're trying to calculate cost and values of different, like maybe 10 different foods. I tried to write a Python program that would calculate this well, and it'd run through all the possibilities and just run through every single reasonable idea within incremental units, and it would take, it would take to like 10,000 years or something like that. It would take forever. I think it was 100 years. I think it would solve it in, which would be great, but I don't have that kind of time. So, so how many units of each substance would she purchase in order to minimize cost? What is the minimum cost? And that's why this math is helpful, because it helps us do things that a computer would take a million years for, or at least 100 to 1,000. That's an order of magnitude anyway. I encourage you to wrestle with this to see if you can figure out exactly what to do here. It's kind of a bit of mixing and matching to do, but I want to give you this general start to say, hey, we want to figure out that we want to know that A and B are the things we're trying to vary, that we're trying to change the amount of food we get from A and the amount of food we get from B. And those together will determine how many carbohydrates and protein and all that, and how much protein we get and all that. And so we need to make sure that Mary is varying those two. Those are the two things under her control. Those are the two variables. Okay, so if you don't want to figure it out on your own, you don't want to get the joy of discovery, or if you have tried it and you just can't figure it out, that's fine. Well, let's try this. Let's look at this. So we want to make sure our two variables are A and B. So we're going to change A and B up to get different results. So A and B will be our axes. Those will be the things we change up. Now we're going to mix and match a little bit to figure out some information. So what do we know? We know that we need at least 24 units of carbohydrates. We need greater than or more. So we need greater than or equal to the amount of carbohydrates we need. It needs to be greater than or equal to 24. Okay. Well, then how many carbohydrates do we have in terms of A and B? Well, if I want to think about it that way, I could say, well, every food A gives me 3 carbohydrates, and every food B gives me 2 carbohydrates. That's another one. So let's see, 3A plus 2B, that will give me the total number of carbohydrates I want. Now that gives me the total number of carbohydrates. And I know that carbohydrates needs to be greater than or equal to 24. So I know that 3 times A plus 2 times B, that has to be greater than or equal to 24 units. So 3A plus 2B has to be greater than or equal to 24. That's one equation. So that helps us deal with and take care. If this is true, 3A plus 2B is true, is greater than 24. If we keep this under control, then we will always have enough carbohydrates. Okay. Now how about protein? So we need 19 units of protein. So we need greater than, the protein needs to be greater than or equal to 19. And let's see, how do we find the protein? The protein gives us, let's see, food A gives us 4 units of protein, and food B gives us 1 unit of protein. So 4A plus 1B, 1B equals the amount of protein we get. Okay, so if P equals 4A plus 1B, we can say 4A plus 1B equals, or it has to be greater than or equal to 19. Okay, so if we keep that under control, we'll make sure that we always get at least 19 grams of protein. If we have 4 times the amount, if we have 4 units of A for every unit of B, and that's always, that gives us a total of 19 units of protein. So that makes sure we always have enough protein there. Great. So that takes care of carbohydrates and protein. What are the variables that they have here? They say that we need to have, let's see, prices. $1.40 per unit for A, and 80 cents per unit for B. Okay, so let's go ahead and check that out. So let's say we need to have $1.40 per A and $1.80 per B. So $1.40 times A plus 80 cents times B gives us the cost. Let's call that, just make that dollar sign, because we can use any variable we want for the variable. Anything we want. So I'm going to use this dollar sign as our variable. Okay, and so from here, if we graph these two equations and then figure out which point on the graph gets us that minimum, or gets us the least amount of dollars, then we'll be good to go, because whatever point that's shaded will always be will give us enough carbohydrates and enough protein. Let's look at this on the graph a little bit for a second. So let's look at let's make this one over here. Let's make that blue, and then I'm going to go over here and make this and look at the purple one for a second. So 3a plus 2b equals 24. If I want to graph this in terms of a, I could say 3a is greater than or equal to negative 2b plus 24. Divide both sides by 3. Divide both sides by 3. So a is greater than or equal to negative 2/3 b plus 24 over 3, which is just 8. I don't know why I wrote that. It's 8. So that'll be what we graph. So let's graph that. So let's make this graph a little more proper, because it's a little bit skewed. Hold on. So we've got okay. Let's see. We've got that, and we've got this. There we go. This looks better. Okay. So let's see. We start with 8 and go negative 2/3. 1, 2, 3, 4, 5, 6, 7, 8, and then rise in negative 2, fall 2, and run 3, and so on. Okay. And we can just graph that. Let's see. That's greater than or equal to. There's our point there. And here's, actually, I'll get that in a second. Actually, I won't mention that just quite yet here, because we need to. That's it. It's gonna be a solid line because it's greater than or equal to, and the side we shade is, let's see, that's A. This is B. The side we shade is determined by the point 0, 0. So let's plug in 0, 0 to figure out what point that is. 0 is greater than or equal to negative 2/3 times 0 plus 8. So it gives us 0 is greater than or equal to 8. 0 is not greater than or equal to 8, so that means we need to shade the other side, this side over here. Now here's, actually, I'll grade. I keep wanting to say something, but I'll say it after I graph the blue line. And I guess just to keep things distinct, we can make this green. There we go. Green is for growth and for money, as my friend in college said. He was an economics major. Funny to say, I was the one who said that green is for money. He was the one who said green is for growth. Okay, so 4a is greater than or equal to negative b plus 19. And let's see, we say that a is greater than or equal to negative 1/4 b plus 19 over 4. And that gives us, we'll go ahead and graph that. So that's negative 1/4. Yeah, so we start with 19 over 4. 19 over 4, just to be clear, because I don't want to make mistakes, is 4.75. So 4 3/4. 1, 2, 3, 4 3/4. And we fall 3/4, and we'll fall 3, run 3/4. Yeah, so we'll run 3, run 4, fall 3. Run 4, fall 1. Yeah, run 4, fall 1. Run 4, fall 1. Okay, and so on. Great. So then we do, this will be our line. It's a solid line. now to figure out where the blue line goes, how to show the blue line, we'll just plug in let's see, we'll try to figure out what happens when we plug in the point 0, 0. So put in 4 times 0 plus 1 times 0 is greater than or equal to 19. So we get, let's see, that's just 0 is greater than or equal to 19. 0 is not greater than or equal to 19. So we can just say it does not include that origin point, which means it goes up in this direction, just like this. Okay. So you can see that the place where it intersects, these two graphs intersect, is all the way up here and all the way down that way. So these are all the possible things that she could purchase. And you can probably imagine as you get more A and you get higher in A and further in B, you get to points that cost more. And so we're trying to find a place that's pretty close to the origin, maybe as close to the origin as possible in some ways, to figure out what is the least expensive option. Okay, so but before we get to there, just one clarification point. We've got values, some of these values, like on the left hand over here, we've got values that are less than 0 in B, and we've got values that are less than, we're going to get to values that are less than 0 for A on the right side. That doesn't really make much sense, does it? Because it doesn't make much sense to be consuming a negative amount of B to gain money, or to be consuming a negative amount of A to get money. That doesn't really work with us so well. It doesn't jive so well. So we got to assume from the outset we don't have a negative A or a negative B. We only have positive numbers. So in that way, we're going to limit our possible answer set to all the positive A's and positive B's, so everything in quadrant 1. So that makes this right here the range of our answer set. This right here, just like that. Okay, so our points, the corner-y points that we have here are right here, and right here. So these are the points that are the kind of the differentiators, the unique and special points in this graph. And so we need to figure out which of these will cost the least amount of money. Do we just go all in and just buy a bunch of A? Do we go all in and buy just a bunch of all B? Or do we go this hybrid option that tries to balance both of them as best as possible? And so that's what we're going to decide here. So first of all, we got to figure out what these points are. Let's see. We'll figure out what these points are. So we got to find the intersection. Let's start with this point on the far left, the place where the purple line crosses the A-axis, or in some ways the Y-axis. If we want to figure out where it intersects with the A-axis, we've got to plug in 0 for B. So we'll say 3A plus 0B is 24. So in other words, 3A is 24. Or A equals 8. And that makes sense, because you can see if you count up, it looks like it counts up to 8 on the A-axis. So we'll say this is 0, 8. And let's see, down here, we'll plug in, let's see, we'll try to figure out where it is we're trying to figure out where that blue line crosses the B-axis, or the X-axis. So we'll say this is this blue line. Let's see, if we're trying to figure out where it crosses the X-axis, we have to figure out where it's Y, or A equals 0. So plug in 0 for A. So we get 4 times 0. This would be 4 times 0. 0 plus 1b equals 19. And, well, okay, so that just makes it b equals 19. And so this point down here at the bottom, this would be the points 19, 0. I hope it's not confusing. I kind of structured this in a really odd way. I put it, maybe I could have made it clearer that I made the coordinates BA, not AB. I hope that doesn't throw you off too much. The coordinates are BA. Okay, so those 2 points, we got 2 points, and now we need to find that third point, that orange point in the center. To find the orange point, we got to figure out the intersection of the 2 lines. So let's say that let's figure out the intersection of these 2 lines just by trying to combine these 2 in like a system of equations. And again, we're going to use equations instead of inequalities because we're trying to find the intersection of the actual lines. So I'm trying to find the intersection of the shaded areas. So let's say 3a plus 2b equals 3a plus 2b equals let's see 24, and then 4a plus 1b equals 19. Okay, so this is a normal systems of equations problem. We can just multiply the 1b by 2. So this gives us, we can change this to 8a plus 2b equals 38. And let's see, I can take care of that line. I just multiply that second line by 2 and that second row. Does this look familiar at all? We're going to subtract these and get something that is, we'll get negative 5a equals negative 14? Yeah, negative 14. So this looks very familiar, in fact. So a equals 14 over 5, which is about, that's 2.8. That's 2.8. And then we have, we'll plug that back in to one of these equations. Let's say we'll plug it into the second one originally. So 4 times, let's see, that'd be 14 over 5 plus 1b equals 19. So 4 times 14 over 5. Let's see, 4 times 14. Oh, nope. 4 times 14 divided by 5. That gives us 11.2. So 19 minus 11.2. Solve that equation. 7.8 is what we're looking for. So b equals 7.8. What this means is that our points is the points 7.8, 2.8. Okay. 7.8, 2.8. That's our point on that's that cross point there. Okay, so we just gotta figure out which of these 3 points cost the least amount of money. Okay, so we'll just plug them in and see what we get. So let's say we have let's just make it a system of equations. Well, let's just put a formula in here. 140 times a plus 0.8 times b, and that should be, we're trying to get the smallest amount possible. Okay, so if we say, let's say that a is 8. I really hope I'm not confusing here by changing the numbers. 8, let's make that store as a, and then 0 store as, oh no, that's not what I want. 0 store as b. Not n, please, I just want b. I've been faster the other way at this point. And so this one would cost $11.20. So if we went with just 8 A's, we just bought 8 A's, that would give us the total amount of nutrients that we need. That'd cost us $11.20. That's that cost. How about the 7.8 and 2.8? So 7.8, they're going to store that as A. This is probably not the fastest way now that I'm thinking about it. Oh well. No, the 7.8 stores as B. Sorry, 7.8 stores as B. I'm confusing myself at this point. And how? And then 2.8 is A. Yeah, 2.8 stores as A. Okay. And then I'll run through the calculation again. And we get $10.16. That's a better price for this. So that's what we want. We want that better. So this is more preferable. This second option is more preferable to the 1120 option. So we kind of maybe want to prefer that a little bit. You can kind of tell the one that's going to be the best is the one that's probably going to be the closest to the origin, or similar, or something like that. We're going to look at that maybe even more closely in this next question. The question after this one. But to finish this one up, let's start with 19 stored. Let's start 19 store B, and then 0 store A, and we'll run that calculation one more time, and we get that costs $15.20. So if we were to live off just B, you would have that would cost $15.20. Okay, so all that said, the one that's cheapest of these 3 options is the one that costs $10.16. That hybrid option in the middle. So if we eat 7.8 of item B every day, and then 2.8 of item A every day, then we'll have the least expensive option. So that's the way we should go here. So 2.8. So that Mary should purchase 2.8 units of food substance A and 7.8 units of substance B. And the minimum cost is going to be $10.16. $10.16. And that's it. That's the answer. So yeah, it's about again, the graphical way of doing this makes it a lot more visually helpful as the possible solutions. This eliminates quite a huge amount of number crunching in order to find the solution. So, okay, number 11. A theater is presenting a program on drinking and driving for students and their parents or other responsible adults. The proceeds will be donated to a local alcohol information center. Admission is $4 for adults and $2 for students. However, the situation has two constraints. The theater can hold no more than 210 people for every 2 adults. More than 210 people. And for every 2 adults, there must be at least 1 student. How many adults and students should attend to raise the maximum amount of money? Okay, so let's see. We've got to let's first start with the constraints. We'll deal with the money later. The money is like the last thing we deal with. Let's first deal with the actual physical constraints that we have to follow. So let's see. The total amount of people has to be less than or equal to 210 people. So we'll say people is let's say adults and students. Let's say that's what it is. Let's kind of partition this off real fast. So we'll say adults plus students has to be less than or equal to 210. Okay, that's simple enough. And then there's and then for every 2 adults there must be at least 1 student. That makes sense because you want to emphasize this is for students. So that means that for 2 adults, oops. So let's see, for every 2 adults, the 2 adults has to be less than or equal to the number of students. No. So 2 times. So that means if you had the 2 times the number of students, the number of adults has to be at least 2. So normally an equation should be adults and students would be 2 times the students. That would normally be the number of adults has to be 2 times the students. But we want to have at least 2 students for each one of them. So that means we have to make it. So that means we would emphasize more students. We would have at least 1 student. So that means if we have an excess of students, that'd be okay. So that means if we have greater than or equal, if it also is less than or equal to 2 times the students, then that's great. That's wonderful. So it has to be at least 2 students per adult. Good. So that means there's at least 2 students, and then there's 1 adult on the one side. Great. So those are 2 equations. We can deal with those. Those are 2 variables, and then we're going to try to figure out what these constraints kind of hold for us, and figure out what are our best options to try. Okay. So we need. Let's see. What do we need to do? We also just some obvious things. The adults has to be greater than or equal to 0. We can't have negative adults, and the students has to be greater than or equal to 0. So we can have negative students. Okay. Let's go ahead and kind of get a general graph of what this looks like. So we would have, if we were to graph something like this, we would want to start with just doing the first quadrant, because it's going to be adults is greater than 0 and students is greater than 0. Okay, so we'll say that, let's say this is the adult axis, and this is this. No, let's make this the student axis. Not for a hugely important reason, but I think students will rise faster than adults. That's kind of what we want, and usually the y-axis goes. These are the higher numbers. Anyway, doesn't really matter. Doesn't actually matter. So students has to be to rewrite these equations in terms of s. We would take this. I'll change the colors of these. This becomes. Let's make this blue. Let's make this one. I don't know. Let's make it. Let's say light green. Sure. So we'll say all adults. We'll say the students has to be less than or equal to 210 minus a, and so that means we start at 210. So let's say this is 210, and then we do minus a, and so that we got minus 1, so perfect diagonal line, something like that. And then we have, let's see, a is less than or equal to 2s, or in other words, let's see, a divided by 2 has to be less than or equal to s. So we'll say s is greater than or equal to a over 2, so 1/2 a, so it kind of goes something like this. This is where that graph goes. Okay, so these are the kind of constraints we're dealing with here, and so let's see. Let's look at the shadings for these. If s is less than 210 minus a, let's plug in zeros for this. Does 0.00 work? If I do 0 plus 0 is less than or equal to 210. Yep, that makes sense. That works. So I can shade in all of this portion that's near the 0, including this portion down here. And then for a over 2, a is less than or equal to 2s. We'd say 0 is less than or equal to 0. Oh, it hits the origin, so that doesn't work. Let's try 0 for a and 1 for s. So 0 is less than or equal to 2 times 1. I'm trying the point 0, 1, if you're curious. And so 0 is less than or equal to 2. So that is a true statement. So that means we cover this point, the point 0, 1. So that means we're going to cover all of this up here. All this up here. Okay. So our triangle is that neat section in the middle. We've got these three values, and our goal is to maximize money. We want to have as much money as possible from all of this. And you can see there's a couple options of ways we can do that. I probably shouldn't erase all that. I'll just undo that because this is important stuff. Okay, so we've got 3 options, and we're going to figure out which of these three options would give us the most money. The first option is just to have no students and no adults. Well, that'd work. That'd be less than 210 people, and the number of students and adults would be appropriate. We could also have 210 students, because that would max out the number of students we can have, and it would it would max the number of students. There'd be no adults. The number of students is definitely more than the number of adults by 2 times, so that works out great. But there's that option too. You'd probably get more money than if you had no one in the room. And the last option is this hybrid option. I don't know what that point is. We need to figure out what that point is, and then we can test that. So this is the value 0 to 10. This is the value 0, 0. And then we can test that final value in a second. Or we can test it now. So we need to figure out what that point is. Let's see. If we say a plus s is less than or equal to 210, and then we say, let's say if we want to find the intersection of the 2 lines, we'll use equal signs. A plus s is equals 210, and then we'll do a minus 2s equals 0. I just took this equation over here and I modified it. I just brought 2s to the left real fast. So a minus 2s equals 0. So this would be, if I want to solve this like a system of equations, I can subtract both sides, subtract all these. So that gives us 3s equals 210, and so s equals 70. Okay, so we have s equals 70, and then we need to solve for a. So a plus s equals 210. So let's say this is a plus 70 equals 210. This would be 210 minus 70. This would give us 140. Okay, so a equals 140. So if we had 140 adults and 210 students, then we would have exactly the right amount. I said 140 adults and 140 adults and 70 students. Then we would max out the place, and we'd still follow the rule of having enough students in there. So we would have enough students, the proper ratio of students to adults. So let's see, this would be 140, and then 70. Okay, 140, 70. Oh, that's somewhat clear. All right, so now we just got to figure out which of these would give us the most money. So we've got three options, and the money portion is $4 for adults and $2 for students. Okay, so let's see. If we had, so it's 4 times, so 4A plus 2 students equals the amount of money we make. Is that right? Is that what we did? Yeah, 4 for adults and 2 for students. So if I just plug in these numbers, if I plug in our values, well, if I plug in 0 and 0, if I have an empty house, 4 times 0 plus 2 times 0, that gives us $0. So obviously this function here, this is not going to be the most, having an empty house is not going to give us the most money possible. But how about 210 students? How would that work? So if we had 4 times 0 adults plus 2 times 210 students, that would give us the amount of money. So the number of money would be 420, blaze it, number of dollars. So that'd be 420, and that would be, that's a pretty sizable amount. But can we get more if we do 140 students and 70 adults? Or 140 adults and 70 students? Is that right it is? Yeah. 140 adults and 70, no. Yeah, 140 adults and 140 students, 70 adults. Did I follow this rule right? The rule is, it should be hold more than 2 adults, and for every 2 adults, there has to be at least 1 student. Okay, so it is 2 adults to 1 student. I thought it was like, you have to have like 2 students for 1 adult. Okay, because that would make more sense in my head. You have to have 2 students per adult, but that's the Christian Ministries guy in me, not anything else. I guess actually you want 5 adults to a student, but that's a different story altogether. 140 times the number of adults would give you, sorry about the tangent, 4 times 140, 140 adults, I'm just checking my work in my head, plus 2 times the 70 students, that would give us, let's see, they would give you 560 plus 140, but I think I'm doing that correctly. That'd give us $600. So this option gives us $600, so which is definitely the most money-making situation. And you can kind of see that because it seems to be the one that's furthest away from the origin, and some kind of sort of furthest away from the origin. Considering that an adult is worth twice as much as a student, this is pretty ideal in a sense, even if it's not technically as far away as the students is. The 0 to 1 to 10 is still pretty far away. Anyway, all I'd say, this is the most cost-effective option. This is the most revenue generating option. So if you want to advertise to people, you really want to make an advertisement that says, "Hey, get your parents and come over to this thing," because you want 2 adults for every single student. Yeah, make it a public activity. You want 140 adults and 70 students. That's kind of what you're going for here. You want to, I mean, sure, it's for the students, but you want to jam-pack this place with adults, as many adults as you can, to get this thing to work. That's our goal here. Anyway. Alright, question 12. Refer to the following linear programming problem to answer the question below. So it gives us an objective function, f equals 5x plus 20. That'd be the way to find the solution. And then the constraints, 2x plus y is less than or equal to 12, 3x plus 3, or x plus 3y is less than or equal to 12, and x is greater than or equal to 0, and y is greater than or equal to 0. So these are our constraints. You can see immediately that we're dealing with quadrant 1. Before we get too deep into this, we're dealing with quadrant 1, and we have 2 real actual lines we need to work with and shade with. Okay, so it's asking which of the following is not a corner point. So we need to find the corner points of this. Now remember, when we deal with a corner point is one of the corners of an actual solution. Not just any of the corners, just the corner of the actual solution. So let's graph this and find the solution so we can find the corners of it. Let's do this. So to do that, I'll start off with the normal graph. I'll start off with a graph of 12, because this is going to get pretty tall. And then I'm going to make a, let's see, this will be my y-axis. And then I'll make an x-axis. And I'm drawing it pretty small everywhere except for quadrant 1, because I know it's going to be just in quadrant 1. So this is my x-axis. Okay. So we've got let's see. We've got 6, 0. Oh, we've got these 2 equations. So we've got x is greater than or equal to 0 and y is greater than or equal to 0. So we're going to start off by saying 2 of our lines are just the axes. And we're going to shade everything just in quadrant 1. That's kind of the preliminary presupposition here. Okay, and then after that, we're going to deal with 2x plus y is less than or equal to 12. Let's do that one in green. So this becomes y is less than or equal to negative 2x plus 12. And then we'll do the second one in blue. We'll say that is 3y is less than or equal to negative x plus 12, or y is less than or equal to negative 1/3 x plus 4. Okay, so those are our two lines. Let's go ahead and graph them, and so we can get a kind of idea of where they belong. Okay, so we've got y equals negative 2x plus 12. So start with 12 and go negative 2. You could also graph them according to the intercepts, but I'm just graphing according to slope-intercept. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then negative 2, negative 2, negative 2. So we're gonna graph this line down here. I'm gonna keep it in the first quadrant because I know that's just gonna be my solution. It's gonna be in that first quadrant. There we go. And there we go. And so we're gonna figure out which side we're gonna shade in. We'll do that in a second. But first we're gonna graph the second equation. Y is less than or equal to negative 1/3 x plus 4. This is supposed to be an x here. Negative 1/3 x plus 4. So start at 4, and so we'll go, let's see, 1, 2, 3, 4, and then fall 1, run 3, fall 1, run 3, and so on until we get to the end. There we go. So this is our second line. And again, I'm just ending at the quadrants. I'm starting and ending at the end of the quadrants because I know that we're not going to go anywhere outside those quadrants. Okay, now let's see which way to shade. So let's see. If we did the green line, we did 0 is less than or equal to negative 2 times 0 plus 12, which would be 0 is less than or equal to 12. And let's see, 0 is indeed less than or equal to 12. So that means that we're going to shade everything on the inside. So all of this and all of this. Okay, and then for the blue, let's see, we'll do 0 is less than or equal to negative 1/3 times 0 plus 4, which is the same thing saying 0 is less than or equal to 4, which is indeed the case. 0 is less than or equal to 4. So we'll shade the side that has the origin in it, the 0 part. So that gives us this right here, this lovely little cross section, which means our answer set is this right here. This right here. So if we can figure out these points, we know all the corner points. Again, this point and this point, these are not corner points. We don't care about those because they're no help in us actually figuring out something practical with this. So we're gonna leave those 2 points out. Okay, but as far as these points go, let's see. We got 1, 2, 3, 4. We've got the point 0, 4, and then we've got, let's see, 1, 2, 3, 4, 5, 6. The point 6, 0. And then let's see, we've got the point 0, 0. So those are 3 of our points right there. And let's see. Let's see. We've got yes. So we've got let's see. We can take 3 of these off so far. We can say 0, 4, 0, 0, 6, 0. And now we need to figure out where this fourth point is right here. This point right here, whether that's 3, 6 or 4.8 and 2.4. Let's do that. To figure that out, let's figure out the intersection of those two lines. So we'll say we've got these two lines here. We need to figure out where these 2 lines intersect, and we can do that through just any sort of form of solutions. I will go ahead and use elimination because that's pretty straightforward. 2x plus y. Let's say equals 12 because we're trying to solve for the lines, and then we'll say x plus 3y is equals 12. But I'm going to multiply the blue side by 2, the blue equation by 2, and that gives me, let's say, 2x plus 6y equals 24. Okay, that way the x's are all lined up, so we can go ahead and subtract both. So I'll do subtract, and that gives me, gives us 0 minus 5y equals negative 12, and so I divide both sides by 5, we get 5, or we get y equals 12 over 5, which is 2.2 and 2/5. So it's 2 and 2/5 or 2.4. So we can kind of figure out which one this is already. Let's finish it up just to be clear. So we've got x plus. Let's just plug the y equals 2.4 back in. So we get x plus 3y. X plus 3 times 2.4 equals 12. Is that right? Yeah, it's 12. And let's see. So we've got let's see. That'd be x plus. Let's see. That'd be 7.2, I believe, and equals 12. Yeah, 7.2, and then we subtract 7.2 from both sides, and that gives us let's see. So 7.2. That gives us x equals, let's see, 4.8. Just what we expect. Yeah, 4.8. So that means x is 4.8 and y is 2.4. That means this is the point. This is the point. 4.8 and 2.4. And it looks about right. It looks like it's roughly in that range. Yeah, it looks about right as the location of it. Because that's about 4.8. This is about 2.4. That looks good. So 4.8, 2.4 is the last one, which means that B3, 6 is the one that is odd, the odd one out. Cool. So that is this lesson. This is the last lesson of the chapter. I hope this was somewhat a little more straightforward. If, again, as always, if you have any questions, please let me know. I'm here to help you however I can and assist you any way you'd like. Just let me know. And yeah, I'm looking forward to seeing your good work. Thanks for all you're doing. This has been a lot of fun. Just a whole lot of fun.